Welcome back. We're in the second section of probability, and we're talking about the addition rules tonight. Some properties to take a look at, and check on the pen here. Yeah. Okay. Any event, and that can be outcomes, it can be a subset of outcomes, or the sample space, excuse me. Remember, any event has a probability between 0 and 1 inclusive. Could be 0, which means it's impossible. 1 means it's definitely going to happen with certainty, or anything in between. Number 2, the probability of anything in the sample space happening is a 1. It's a sure thing. Good bet. And the third one says with the empty set, in other words, nothing happens. The probability of nothing happens from that sample space is 0. 3 good things to remember, and those can be handy at times, as we'll see. If the event includes the entire sample space, we saw that back here, entire sample space, the probability is equal to 1. You can write it as 100% if you like. You can write it as 1.0000. It all means the same thing. Even if you write it as 17,000 over 17,000. If you had 17,000 events in your sample space and you want the probability that one of those 17,000 happens, there would be a probability of 1. And let's move on here. Okay, complement. Now, this notation they show right here is not the only notation you might see for complement. Complement can be seen a bunch of different ways. Some of the ways I've seen it are this E with a squiggle in front of it, a tilde. I've seen it with a minus sign in front. I've seen an E with an apostrophe in front of it. It all depends on the author and what they like. All those are possible. But the important thing is, when you're thinking of your sample space, there are 2 things that are exact opposites, E and not E, the complement of E. If you put those 2 together, either E happening or E not happening, you get the sample space. Another way of putting it is, if this is your sample space, and this is a picture of your event, everything that's not in the event is out here, and when you put those 2 together, or glue them together, or throw them into a bucket together, you get the entire sample space. Remember, the probability of anything, either of those 2 happening, is equal to 1. Good thing to remember. And there's another one. I forgot about this one. E bar is another way of saying complement of whatever E is. That would be everything. This would be the equivalent of saying E is not happening. Either E happens or E does not happen. A couple of samples here to give you an idea of what we're talking about. Describe the complement of each of the following events. Here's a good chance for you to maybe hit pause, write down what you think the answers might be, then we'll check your answers. choose a vowel from the English alphabet. Well, if we go with the standard vowels, A, E, I, O, and U. I know there's some others that are considered it from time to time, but those are the standard ones. Now, what's the complement? If this is E, what is the complement of E? We're talking about the English alphabet. So A is over here, so it's not over there. You'd have B, you'd have C, D, everything except what's in there. Those two are complementary. There's nothing that's in both those sets. Together they make the entire sample space, which in this case is the English alphabet. So if you were working for a printing company and you got those 5 letters for your printing machine, and you got these 21 letters, then you can write anything you liked. Part B, 31 students in your statistics class. That's not too far away from our list, really. 15 are sick out with the flu. So what could that look like? You could always draw a picture, right? Draw a picture. Get used to that. So here's the stat class, and here's the set of sick people, and this group would be the ones who are not sick. Notice that if you take the sick ones and add the ones who are not sick, you get the entire stat class. Check that off. Next. C. In your area, 91% of the phone customers use Phone South. That sounds a bit like Bell South, doesn't it? But anyway. So, here are the phone customers. Sample space equals phone customers. Shorten that. Some of them use Phone South. Phone South customers. What's the complement of that? I'm going to shorten this. Phone customers who do not use Phone South. All right. So there are the 3 answers. Did you get them right? I hope so. Next, we've got outcomes in the event. Just as a reminder, if you put an event and its complement together, you get the entire sample space. And another thing to think of is if you're thinking of probabilities, for example. The probability of that event happening, and add to that the probability of its complement, the opposite. Since those are the only things that can happen, and E and EC together make up the sample space, they're equal to 1. Not only that, the sneaky thing you get from that is that if you want the probability of complement, if you do a little bit of algebra here, you could get that in reverse, you might say, by taking the probability of the event and subtracting it from 1. So if this is what you want right here, you can do it this way. Just subtract the probability of E from both sides, you've got your new equation. Or you could do it this way. Subtract the probability of the equivalent, or the complement, excuse me. But if you're going to remember something, remember one equation, not three. Just use a little bit of algebra and you can get the whole thing. Remember, the probability of 1 is that you're going to get something from the sample space. So there's the formula. That's one to write down on your index card or whatever you're using to keep your notes on. So let's take a look at using the complement rule. You say there's a 35% chance that you'll fail the upcoming test. What's the probability you'll pass the test? Well, you can draw a picture, you can draw that in your head or whatever. Here's a test sample space. Chance you'll fail there. Chance you'll not fail here. Since this is 0.35 or 35%, what's the rest of it? Remember, the probability of fail plus the probability you don't fail is 1. So you just subtract the 0.35 from 1, and this will be 0.65, or 65% chance of passing. That's part 1. Part 2. If there's a 5% chance that none of the items on the scratch-off lottery will be a winner, no winner, what's the probability that at least one of those scratch-off items will win? Well, the event is winning. E complement is not winning. This is 5%, also known as 0.05. So what's this one? This would be 95%, or 0.95 if you wish. And there's the wrap-up. And so you have a better than 50-50 chance of passing the test, and you have 95% chance of at least one winning scratch-off on your item. Next one, roll a pair of dice. So you've got a pair of dice. Good luck with this one. I knew this would go awry somewhere. There's your die. I know, this will make it look better. Anyway, I'm going to say we've got 2 of those. I'm not going to try it again. What's the probability neither die is a 3? Well, this is one case where you want to sort of sneak up on the answer. So first of all, what's the probability of a 3? Because what we want is the probability that it's not a 3. So, the sneaky way of doing it is find the probability of 3. Well, how can you get a 3? We've seen this before. There are 36 items in the sample space. How many ways can you get a 3? You can get a 3 by having a 1 on the first one and a 2 on the second one, or a 2 on the first and 1 on the second. The only 2 ways it can happen. So the probability of 3 is 2 ways out of the total of 36 ways that you can roll a pair of 6 standard die. But that's not what we wanted exactly. We want the probability that's not a 3. Neither dice is a 3. Well, I was looking at it from a different direction. Oh, we'll do this twice. So, probability of not a 3. Then we'll get to the actual question itself. So the probability of a 3 is 1 over 18. The probability not 3 would be 1 minus 1 over 18, or 17/18. Now we'll get to the real problem. What's the probability neither die is a 3? Neither die is a 3. So we could list all the outcomes, but what's the complement? The complement is either die is a 3. So check to yourself how that works. Either die is a 3. So what do we have? Either die is a 3. Remember, got 1, 2, 3, 4, 5, 6 for die number 1. For die number 2, for each one of these, we've got 1, 2, 3, 4, 5, 6. And this also has all 6. This has all 6, all 6, all 6, all 6. So either die is a 3. So if it comes up here, how many ways can we have a 3 there? We can have 6 ways for die number 1, and we're going to have 6 different results here where this comes up. Six ways for die number 2. This doesn't look like a 1. There we go, that's a little bit better. So we've got 12 here, but remember, we could also have a 3 on the first and a 3 on the second. So when I add up those two, I added this combination twice. So there are actually 11 ways we could have this. So the probability that either die is a 3 would be 11, 11 over 36. So the probability that neither one is a 3 would be 1 minus 11 over 36, or let's see, 25/36. Is that right? Check this real fast. Yeah. And that would be our answer. All right. All right, there's a picture of our die. We have one of the sets of 3 here. Let's see. There we go. There's one set, there's 6. There's another 6. And these are the ones that are repeated. So there's our 11 over 36, which is our complement, and 25 over 36, the numerical equivalent, the probability that neither die is a 3. Now here is the addition rule that we've been getting to. If we want the probability of two events, and we want the probability that either one of those events happens, the addition rule says just add the two probabilities. However, notice in the last one, we had threes happening two different ways. So before you just add those and write that down as your answer, we have to subtract the probability of both of them happen at the same time. Because when we get this, we've added this probability twice, because we'll be adding it there again. So if you see an or here, add the probabilities, but subtract the probability that both could happen at the same time because you've added them in twice. You have to subtract them out once to get the total. So here's an example for you to follow. Sarisa, I guess, is looking for a new condo to rent. The realtors provided her with 17 available properties, and the list contains the following. Close to the subway, there's 6 of them. Low maintenance fee, 7. Green space, 5. Newly renovated, 2. Close to the subway and low maintenance fee, 2 properties. Green space and newly renovated, 1 property. So she selects the first condo they visit at random. What's the probability that it's either close to the subway or, keyword, or has a low maintenance fee? So we want the probability that it's close to the subway or low maintenance. The OR says use the addition rule, so you'll have the probability that it's near the subway plus the probability that is a low maintenance fee. But it's possible that you might have a property that has both those. So you want to subtract the probability that's near the subway and low maintenance fee. So what do we have? Well, first, we've got 17 available properties. So each of these probabilities is going to have a 17 in the denominator, right? And this one as well. Now how about close to the subway? Close to the subway, there's 6 properties. So this will be 6/17 is the probability that the random property is close to the subway, plus, got the addition rule. Now, low maintenance fee. 7 of the properties have low maintenance fee, so that'll be 7 out of 17. And are there any that are near the subway and have a low maintenance fee? Well, as it turns out, there are 2 of those. So we'll subtract those, because when we got the 6 here, that included these 2. When we had the 7 here, it also included the 2. We don't want to add it twice. So 6/17 plus 7/17 is 13/17 minus 2 will be 11/17 is the probability. And we can change that to a decimal. There we got 6/17 7/17 minus the double added one, where both of them are true, 2/17. There's our 11/17, and the decimal version with 4 decimal places. And if you like it in percentages, just move that decimal point 2 places to the right, or multiply that by 100%, and you've got this second version of your answer. Next, I'm going to suggest maybe you want to just pause it here, read through this. It's sort of interesting. It's not something we're going to spend a lot of time on. It gets rather complicated, actually, but quite interesting. There was a lot of controversy at the time. Firestorm of mail, telling her that she was incorrect. Interesting, historically at least, for probability. So let's go on to another example. Using the additional rule for probability again, we're going to, after a vote in the U.S. Senate, it's on a health care bill, doesn't say what year, and this is how the voting went. If a lobbyist stops a random senator, just like our random selection of a property in the 2 slides before, we're going to pick a random senator after the vote. What's the probability that this senator will either be a Republican or voted against the bill? Notice the word or, that's the key. We're going to have the addition rule, E, and F, and we're going to subtract the probability that both of them are true at the same time. So let's look at the table there. First of all, we need the probability of E, which in this case is that they're Republican. So, probability of this random senator being a Republican is, let's look, we've got 50 Republicans. 50 Republicans. And how many senators do we have? We have 100 senators in the Senate. Also, the other probabilities voted against the bill. Voted against. How many voted against? Well, down here, this is the column for the ones that are voting against it. You've got 21 plus 7 plus 4, 32 votes against. So voted against, we have 32 voting against, and again 100 senators. We also need the probability that someone is in both those categories, Republican and voted, let's squeeze that in, voted against. Well, what's that? If we look back here at our table, how many Republicans voted against? Well, here's the Republicans line, and you see over here, there's 7 Republicans that voted against it. So for this third one, we need 7 over. How many senators do we have? We have 100. So for our answer, we're going to take that 50 over 100 plus 32 over 100. These are the Republicans. These are the ones that voted against. And we'll subtract the ones that we've added twice, which is 7 are the senators. So adding the first two, we've got 82 over 100 minus 7 over 100 for 75 over 100, which we could put as 0.75, or we could write as 75%. We've got our answer. So the probability that the senator who was stopped by the lobbyist will be either a Republican or have voted against the bill is 75%. Here's a summary of what we just did. A little bit cleaner, easier to read than my writing, but still the same thing. Next, we're going to roll a pair of dice. What's the probability of getting a total that's less than 4? Total less than 4, or the total equal to 10. Okay, let's take a look. The probability is less than 4, excuse me. Well, how can we do that? We could have a 1 and a 1. If it's a 2, that's good. We could have a 1 and a 2, and that's good. But we could also have a 2 and a 1, because remember, the dice are not the same dice. If we have a red die and a green die, it's a different result. Both of these give us a 3, and those are good. Less than 4, if we roll any other way, we're going to get something bigger. At least one of them has to be a 1, and at most one of them can be a 2. So we've got 3, and if you go back to the last lesson, you'll notice there are 36 ways we can get a result when we've got dice. Now, second, the probability that the total is 10. How many ways can we have that happen? Well, we could have a 6 and a 4, or we could have 4 and a 6, oops, excuse me, and we could have a 5 and a 5. Looks like those are the only ways, right? So 3 over 10, total equal to 10. Okay, that's it. So or, so we're going to add. We also need, what's the probability of less than 4 and 10. Well, if it's less than 4, it can't be a 10. So these can't happen at the same time. So the probability of this happening is 0. So for the final probability, we'll have probability of less, let's put it this way, x. Call x our total. The probability it's less than 4 is a 3 over 36. Probability of getting a 10, 3, oops, how did I do that? Yeah, 3 over 36. And the probability of both, 0 over 36, not a 10. So our probability of the result we're looking for is 3 over 36 plus 3 over 36 minus 0 over 36 is 6 over 36, 1 over 6, or 0.1667, 16.67% is the probability of getting something less than 4 or equal to 10. There are the dice for us. And there's a wrap up of the results we just got. Next, what we just did is we talked about things that are mutually exclusive. Remember? Less than 4 and getting a 10. You can't have those happen at the same time. If two things cannot happen at the same time, they're called mutually exclusive. This can happen, but they both can't happen at the same time. That makes them mutually exclusive. And as you just saw back here, that mutually exclusive is the same thing as subtracting 0 over 36. So if you know they're mutually exclusive, you can find the probability of an OR statement by just adding the first two. I'll give you a hint. This is one that I use. I don't worry about the mutually exclusive part so much, because when I work it out using this formula in general, I go ahead and figure out the first probability, and the second one, and the third one. If this turns out to be 0, I know it's mutually exclusive. They are mutually exclusive, but it's all going to work out in the long run. I don't have to have two formulas to answer one question. So this is what it looks like if this part out here, if that part's a 0. Why have two formulas if you can use one? If you realize they're mutually exclusive, you know that this last one will be a 1. Makes things a little bit shorter. So here's an example we can use. So Caleb is very excited. Know anyone named Caleb? It's finally time to get his first new car. My first car was a Dodge Dart, but it wasn't the first new car. My first car was a Ford Maverick. Any of you have heard of the Ford Maverick? So he narrowed his choices down to 4. It's taken so long, his friends have started to bet on which car he's going to pick. They have given each car a probability based on how likely they think Caleb likes that kind of car. Devin's betting that Caleb will choose either the Toyota or the Jeep. Toyota or the Jeep. Find the probability that Devin is right. So it says Toyota or the Jeep. So what you want is the probability of Toyota or the Jeep. Since it's OR, we use the addition rule. So we'll have the probability of the Toyota plus the probability that he chooses a Jeep minus the probability that he chooses a Toyota and the Jeep. Well, this last one is sort of silly. He's picking a car, not cars. So this part is 0. So all we have to do is get those probabilities, and they're given to us right here. So the probability for the Toyota is 0.40 right there. The probability for the Jeep is down here, 0.35. Add those together, and we have the probability that he'll choose a Toyota or a Jeep. Devin's going to be right 75% of the time. Okay, here's a quick summary of what we just did. And we've got one more example of mutually exclusive events. So there's an exit on the interstate. You know all about interstate exits. From experience, We know the probability of a truck driver refueling at each of the 5 possible gas stations are given in the following table. We'll see that in a minute. If the truck driver will refuel at only one of the gas stations, making them mutually exclusive, he's not going to refuel and then refuel again because he's already pretty full. What's the probability he will refuel at Shell, Exxon, or Chevron? So this is an extension of the addition rule. It gets a little bit more complicated, but because they're mutually exclusive, he's only going to refuel at one of them, then we're going to add those 3 probabilities. So remember, Shell, Exxon, Chevron, we'll add those 3 probabilities. So here we are. The probability of stopping at the Shell is 0.3207. The probability that he stops at the Exxon to get refilled, 0.2793. And the probability that he refuels at a Chevron is 0.1539. I dare you to do that in your head. It's not that difficult, come on, really. Even with the decimal points not lined up, 7, 3, 9, 19th in the first column, and so on. So what's the total? You got it? Write it down. So the total is 0.7539, or just roughly speaking, about 75% that he's going to refuel at one of those 3 stations after the interstate exit. Well, I hope you've enjoyed our next lesson on probability, and I'll see you soon on the next one. Until then, bye-bye.